Welcome to another exercise in the workbook statistics, this time with an exercise focusing on t-test for coefficients and the f-test. Let's have a look at the exercise. The manager of a mall expects a linear relation between the daily temperature and the average spending in the mall's food court. To test this assumption, data is collected for 5 different days. Then our first task, assuming the regression gives you a coefficient of determination of r squared equal to 0.59, conduct a suitable test at an error margin of 5% to check whether the model has significant explanatory power. Part B, in how far will the results from part A change if the acceptable error margin would be 1% instead? And part C, in how far will the results from part A change if the acceptable error margin is still 5%, but the coefficient of determination did result from estimation with a total of 52 observations? Well, let's get right through it. Let's start first with determining the F statistic, which we need for our test in either case. So here the F statistic results from r squared divided by k, the number of independent variables. In this case, from the text we get that we only have one independent variable, 1x, so k is 1. Then we have 1 minus the r squared, and down here n minus k minus 1. N, that's the number of observations, so in the first part it's 5. So we have 5 minus 1 gives us 3. So our test statistic in this regard is 4.3171. In addition, for the test we also need a reference statistic, which for the F test can be gotten as f k n minus k minus 1, 1 minus alpha. K we know is 1, n minus k minus 1 we know also, that's 3. And then I have 1 minus alpha. Alpha, as determined in the exercise text, is in the first part 5%, so we have 1 minus 0.05 giving us the 0.95. So this statistic here, this value here, we have to look up in the table for the F distribution, yielding us a reference statistic of 10.128. Then for the test itself, we can compare test and reference statistic, and we see that the test statistic is smaller than the reference statistic. Whenever this is the case, we cannot reject our H0 hypothesis, and H0 in this case means that the model does not have any significant explanatory power. So that's the situation for an error margin of 5%. Now in part B, we can turn to an error margin of 1%. So the test becoming stricter. That's actually, as I said, we could theoretically use the same test statistic, then look up a new reference statistic. With a new alpha of 1%, we would have the first same values. First two are the same, but then we have 1 minus 1%, so it's 0.99, yielding us here a reference value of 34.116. Of course, this is then again larger than the test statistic, and again, H0 cannot be rejected and the model still has no significant explanatory power. As I said before, if we decrease the error margin, this always means the test becomes stricter, and this is displayed by a larger reference statistic. So if the test is not significant with 5%, H0 cannot be rejected with 5% error margin, it will always also not be able to be rejected at a 1% error margin. The other way around might be possible. Might be that with 10% we could reject H0, the model might have significant explanatory power, but with a margin of error of, well, less than before, it still remains the same. Well, so much for part B. This leaves us with part C. In part C, we actually have to calculate the test statistic anew, because while we still have the same r squared and the same k, we now have a different number of observations. So here we do no longer have 5, we have 52 52 minus 1 gives us 50. So if we then calculate the new test statistic, we get 71.9512. The test or reference statistic also slightly changes. K is still 1, but we have n minus k minus 1, so the 50 here. And we have still the same error margin of 5%. So we have here 0.95. If we look this value up in the table for the F distribution, we get 2.79. So in this case, we can clearly see the test statistic is larger than the reference statistic, than the reference value. This means we can reject H0 and the model has significant explanatory power. So this tells us if we increase our number of observations with R squared remaining the same, then the chance increases twofold that we can reject H0. On the one hand, this will increase the test statistic. On the other hand, it will lower the barrier, meaning it will give us a lower reference statistic. So increasing the number of observations is always a good choice if we want to have a model with significant explanatory power. And well, that's then everything there is regarding the tests, but also what we can learn from the different parts of this exercise. I hope you enjoyed it. I say goodbye and see you next time.